Today, I want to talk about some strategies for lowering operational voltage of organic field effect transistors. And I want to take your nice introduction. This is my outline. First of all, I want to give some information about our institution and current research going on our institution. And I want to give some information, brief information about the conductive polymers. And then I want to give some brief information about organic field effect transistor, and I will continue with the new approach for lowering operational voltage of organic field effect transistors. This is our laboratory capabilities of our institution. We have two main laboratories in our institution. One of them is the nanotechnology and biotechnology institution, and the others is experimental medicine research laboratory. And nanotechnology and biotechnology department has 16 laboratories and one 200-meter square clean room and some characterization facilities, SEM, AFM, and lithography facilities.
Sorry to interrupt you, Dr. Arif, but your slides are not moving.
Not moving?
You have to just not. Sir, you have to just click on the slide which you want to display. We are only on the first slide.
Now?
Now it's, yes, sir.
Okay. Now you can see easily our slides?
Yes, sir. You are in fourth slide. Fourth slide, no? Experimental medicine research laboratory. Yes, sir. You have to just click on the slide.
Okay. And these are our facilities in our institution. And the other facility, experimental medicine research laboratory, we have in this section, we have 18 laboratories, 600 live animals, and transgenic animals, röntgen rooms, operation rooms, living rooms, quarantine rooms, and behavior laboratories we have in this institute. Our research project, mainly we are research on the nanotechnology, metal or metal oxide-based nanostructure fabrication and characterization, and these nanostructures application of gas sensors, organic electronics, kind of OPV devices or organic field effect devices, or sensors applications for liquid and bio applications. And finally, we try to make some kind of prototype electronic devices. Now I want to give some information about organic semiconductor materials. Everybody well know this polymers was known as insulating materials until 1980, but at 80, this three men. This three men showed that polymer can be behaved as a conductive materials, and new conductive polymer materials was discovered by Alan Hager and his co-workers. And this innovation brought to them a Nobel Prize at 2000. These materials have some advantages and disadvantages, but flexible. This materials has many advantages, metallic and semiconductor properties. You can change its metallic and semiconductor properties with doping process, and you can easily coat these materials on any substrate from the solution with a cheap production methods and solubility in organic solvents and variable processability and use of printing techniques, very cheap and very easy techniques. You can apply these materials, and you can say this advantage is low integrated device and circuits, and long-term stability is still a critical point for these near-term conductive or semiconductive materials. And you can see here some examples for the conductive polymers, polyacetylene and polypyrrole, kind of polythiophane. There are many kind of conductive polymer materials. In order to understand of the semiconductive properties of the polymers, polymeric materials, it is necessary to understand the bond structure of carbon. This is the electronic configuration of the carbon atoms, and carbon can make 4 bonds because of the hybridization. 3 of them are called as sigma bonds, and one of them is called the pi bonds. Pi bonds occurs between the perpendicular pz orbitals, and bonding energies is low, less than 4 electron volt. But sigma bonds are very strong, and their binding energy more than 10 electron volts. Pi bonds on the polymer chain gives the conductive properties to these materials.
Arif?
Yeah.
Sir, your slides are not moving, as I guess. You are on 6th slide. Yes, sir. Now it is moving. So you have to just click on the slide which you want to display.
Okay, now it is.
Yeah, organic
Sure.
semiconductors.
Yeah.
Okay, sir. Now you can continue.
Thank you. P bonds on the polymer chains gives the conductive properties to this material, because P bonds can easily affect the external conditions such as light, temperature, or applied potential, and you can move the electrons on the free energy levels. And conjugation is the essential condition for the conductive properties. Conjugation means alteration of the single and double bonds. You can see here the conjugation properties: double bonds and single bonds, double bonds and single bonds. This is should be continued. And then charge can easily move on the polymer chains because of these properties. And here, correlation between the energy levels of the electronic states of an isolated molecule and those of the organic materials. These materials has homo and low energy levels, and between these energy levels, it has an energy gap. LUMO means lowest unoccupied molecular orbital, and HOMO means highest highest occupied molecular orbital. And these molecular orbital levels behave the conduction and valence band, such as behave the conduction and valence band. The magnitude of the energy gap is 1 and 3 electron volt. It is very range. You can easily change the energy gap with some chemical approaches, and this mobility can change 10 power minus 6 to 10 centimeters square also. And this is an example for how a charge move on the polymer chain with alteration of the single and double bonds. Organic semiconductor materials can be used in the very application area, such as solar cells, organic field effect transistors, supercapacitors, lithium-ion batteries, and sensors, actuators, electrode binders, such as medical application and super hydrophobic surface. You can find every research area these conductive materials. And this is an example, thin film formation by spin coating, and you can easily solve this material in the solvent, and you can coat any substrate with the spin coating method. If you want to pass the industrial scale, you can use slot die or inject printing methods. It's very easy and low cost production methods. You can get large scale devices with this coating methods, with these conductive polymers. And now I want to talk about the motivation for the low voltage offsets. Why we want to low voltage offsets. This is an example or first version of the transistor. And this is very big and slow. But these people or scientists understand how can an information stored and transferred, and this information get the first computer and big size computer, and then by the time transistors by time and technology transistors getting small size and fast, and this get small size computers and fast information transfer technologies. Then you can see on the finger, this is the transistors arrays. It has maybe more than 1,000 transistors. This small size transistor technology get flexible screens or small and fast electronic devices, kind of cell phones or fast computers. This technology, for this technology, we need the low voltage transistors. You can get these low voltage properties with the inorganic materials or silicon technologies, but you need to operation voltage getting low for organic field effect transistor to use in these screen technologies or flexible or variable technologies. Organic field effect transistors have drawn much attention due to their advantages in flexible, lightweight, large area, and low-cost natures, which have exhibited high potential in radio frequency identification tasks, flexible displays, sensors, and variable devices. The realization of low voltage operation characteristic requires forming a sufficient charge carrier concentration within the conductive channel at a minimum gate drain voltage. You need a sufficient charge concentration in the conductive channel with the minimum as possible as minimum gate drain voltage. The realization of low voltage organic field effect transistors is in urgent demand for next generation flexible and variable electronics. It is very important. Low voltage organic field effect transistors for the flexible and variable technologies. Although there are several strategies for enhancing the low voltage operation capacity, high K dielectric materials means high dielectric constant dielectric materials, ultra-thin dielectric materials, or electrolyte-based dielectric materials, and interface engineering lots of issues are still unstilled and need to be followed. For example, the use of high-cut electric layer usually leads to a problem of the interface dipole, and this damages the performance of the organic field effect transistors. If you use ultra-thin dielectric layer, using of this ultra-thin dielectric layer is susceptible to rupture and breakdown when of it deform. It's very easily can deform because it's very thin. Offsets based on electrolyte gate dielectric have relative poor operation stability due to the ion migration rate to large interfacial polarity. If you use the electrolyte-based gate dielectric, ions can migrate in the active layer, and this migration can damage the organic field effect parameters. Some interface modification methods like SEM means self-assembly monolayer using of self-assembly monolayer may introduce the interface stress issues and damage the device performance. Although some solutions have been proposed for these problems, such as interface engineering, designing intrinsically stretchable offsets, and improving the interface mismatching, there are lots of further research effort that need to be devoted to the optimization of organic field effect transistors. And I want to give some brief information about the working principle of the organic field effect transistors. Organic field effect transistors has three main layers. One of them is the semiconductor layer. This is active layer. Charge occurs in this layer, and the move in this layer, charge accumulation occurs in this layer. The other important layer is the insulator layer. Insulator layer is very important for to get low operation voltage. Properties and quality of the insulator layer is the main factor for the get low operation voltage. And the other layers is the source drain electrodes and gate electrodes. And when you apply the potential on the transistor, you will see two regime current. One of them is linear regime. This is increased with the applied increasing of the applied potential. The other of the saturation regime. The field perpendicular to current flow generated by the gate voltage, and this is the electric field, transverse electric field generated by the gate voltage, and this is the longitudinal electric field generated by the drain electrode. The field perpendicular to the current flow generated by the gate voltage is much larger than the electric field parallel to the current flow created by the drain voltage. What is the important parameters, performance parameters? These are high mobility, on-off ratio, and threshold voltage. If you want to get a high quality transistor, you should have a high mobility, high on-off ratio, and low threshold voltage. And now I want to give some examples from the literature. This is the summary of the chemical structures and their dielectric constants of common high-cap polymer dielectric materials. These dielectric materials can be used to get some quality organic field effect transistors. These materials, examples for the insulating layer. And this is the one of the other examples from the literature, in this study, PV3D3 dielectric layer or dielectric polymer materials used as a insulating layer, and with this they can get the low operation voltage transistors under the, it can be works under the 3 volt. And this is another example. They used some self-assembly monolayer to lower the operation voltage of the organic field effect transistors, and they can get under the again 3 volt operation voltage with the SEM. And this is the another examples, and this is the ion gel gated transistors. Ion or gel structure, the electric materials used in this study, and with this the electric structure, they get the low operation voltage organic field effect transistors. And now I want to talk about our approach to get low organic field effect transistors. We use gel-like polymeric dielectric materials. We fabricate these gel-like polymeric materials with the PMMA. Polymethyl methacrylate is a well-known dielectric material. This can be used as a dielectric layer in the offset structure, and we use propylene carbonate, and this propylene carbonate is well-known plastic material. We combine these two materials, and we get this gel structure. You can see right side of the slide. This is our gel-like material or gel-like polymethyl methacrylate dielectric material. And how we can apply this material? First of all, we separately coat the source and drain electrode and gate electrode on the glass substrate. We use silver electrodes, and then source drain electrodes on the source drain electrodes P3HD as active layer, coated with the by the spin coating method on the source drain electrode, and the gel this gel sprayed with this bottle on the gate electrode. Then we sandwich the gel between these two substrates, and surprisingly we get very low operation voltage organic field effect transistor with this structure. If you use PMMA as poor PMMA as a gate electrode, the electric material with P3HD, you can get 100 volt operation volt. But with plasticized PMMA, we get under the 1 volt transistor. This is very important for the flexible electronic applications. And you can see here the operation and the transfer characteristic of our transistors. And we characterize the gel structure capacitive properties. Its capacitive property is very high capacitive value, almost 1 microfarad per centimeter square. We can get this structure. The goal of our study is to realize a novel gel-based FET design, including P3HD solution-based sandwich material in ambition in conditions. All experiments conducted in the ambient condition. And this is our other study. We used gel structure again to get and this sandwich structure to get low operation voltage, but we changed the polymers. Instead, polymethyl methacrylate, we used polymethyl acrylate with the combination of the soil oil and the content of the soil oil changed, and we can get a high mobility and low operation voltage with this approach. Relative dielectric constant of the polymer can be decreased by soybean oil dop, and mobility can be enhanced by decreasing the relative dielectric constant, and better insulation property bring about lower off current. This is very important. Better quality interface pave the way for a high on-off current ratio. These are results from study. And this is another approach for the gel-like dielectric material. And we used again polymethyl methacrylate and propylene carbonate combination to get the gel-like dielectric material. But instead, P3HD polymer we used in this study copper phthalocyanine as active layer. Copper phthalocyanine is the small molecule, and we evaporate this molecule coated on the source drain electrode. And in this study, we used interdigitated electrodes as goal. And this is our device structure, and this is the materials. Also, we add some new information in this study because copper phthalocyanine and the P3HD is P-type organic semiconductor materials, and we use N-type semiconductor organic materials with this gel-like PMA approach, because we want to see this material can be work with only P3 materials, or both P and N-type materials can be worked with this approach. And these are results, output and transfer characteristic for both materials. Gel-like dielectric worked very well, and we can get under the 0.8 volt transistor and good transistor behavior linear regime, and you can see easily linear regime and saturation regime from these graphs. And these are the poor PMMI devices. You can see here this device works with 100 volt, but when you get the gel-like dielectric or turn into the gel to PMMA, you can get the 1 volt transistor easily, and this is also same the other organic molecules. For the other organic molecules. And you can see here easily our device structure, copper phthalocyanine coated on the source drain electrode, and we used for this plasticized PMMA spacer, and this spacer thickness is 50 micrometer, and the other contact is coated glass substrate sandwich between these two substrate plastic PMMA. And this is an approach for to explain what is happening in the gel. The dried film can be accepted as a tightly together chain like this. Figure A. Propylene carbonate has two major contributions. First is the polymer chain. Polymer chains remain in a more extent conformation, and second is that its high dipole moment actively contributes to total dielectric behavior. More contribution coming from the propylene carbonate because propylene carbonate has a large dielectric constant. The natural polarity of the propylene carbonate molecules is randomly oriented in the matrix due to the thermal motion or something else. It can freely move into the polymer matrix. And there is no bulk polarization of the propylene carbonate. When an electric field is applied between the plates, preferred direction, you can search the direction of the electric field of orientation of the propylene carbonate molecule develops in time. Therefore, propylene carbonate molecules directly contribute to the total dielectric in addition to the polymetric metacrine. And this is directions of the propylene carbonate molecules, and when you apply the electric potential, this you can change the direction of the propylene carbonate molecules. And there are some results from our experiments. This is the stability experiment. It's very important because we applied voltage on the fabricated devices for more than 5 hours, and this is you can see here after 5 hours the transistor can be works very well. And you can see this is on voltage, this point is off voltage, this point on voltage, this point is the off voltage. We continued this experiment more than 5 hours, 5.3 hours exactly time. And this gel-like structure, we saw this gel-like structure is very stable for the application of some electronic array. And this is, you can see here the electric properties of the plasticized PMMA. And also we conduct an experiment with the cryogenic conditions, low temperature to high temperature, and we get activation energy for the surface of the active layer, interface of the active layer and the propylene carbonated polymetallic metaplate. Finally, we get a high performance organic field effect transistors. We used high K composite polymer gel dielectrics. We use in the study again propylene carbonate as plasticide and polymetallic metacrine as a polymer chain to get the matrix. And we add this gel-like structure, silicon dioxide nanoparticles, to get more stable and more mobility values. And this approach gave me our best mobility value 4.66. This is our record value, and we get this 50% silicium dioxide in the PMMA gel dielectric structure. This gave me. Thank you for your kind invitation, and thank you for your
Thank you, Dr.
listen.
Arif, for such a wonderful talk.
Thank you.
Now it's time of questioning. Do we have questions for Dr. Arif? Please raise your hand.
Thank you, Dr. Arif, for your nice talk. My question is, what role does the device architecture play in determining the operating voltage of an organic field effect transistor?
Can you repeat again? I couldn't understand, please.
What role does the device architecture play in the determination of operating voltage of an organic field effect transistor?
Device architecture. Architecture. If you mean changing the place of the source drain electrodes or gate electrodes or insulating air, it doesn't important for the lowering the operation voltage, because the important thing is the materials what used in this organic field effect transistor structures. If you want to lower the operation voltage, you should get high dielectric materials. It's very important.
Okay. Thank you.
Welcome.
Dr. Vinod, you can ask the question, sir.
Yeah, good noon, sir. I want to ask what about the lifetime stability of OFET devices.
Life and stability.
Yeah, yes, sir.
Life and stability depend on the polymeric conductive polymer materials stability properties only. You have to encapsulate these materials to isolate it from the ambient conditions. But you can see here, if I can open, our approach, you can see here, top electrode and bottom electrodes close together with glass substrate. And there are two spacer the edge of the devices. And with this structure, you also you get the encapsulation structure. Because of that, our structure can work easily more hours. But if you exposure or if you don't encapsulate these devices, polymeric materials can be damaged by the time in several days, maybe.
Okay, fine, sir.